Hi, everyone, and welcome to this RIOT seminar on the 19th of November 2024. My name is Camille, and I'm one of the core team members of the RIOT Science Club, Rotterdam. The RIOT Science Club is an initiative to promote open science practices, and we mainly do this by organizing seminar series, just like today. In a moment, Dr. Peter Clayson will give a talk on multiverse analysis. That's why we're here. But just to make sure everyone has enough time to join the event, we'll start the talk in about 5 minutes. In the meantime, have a look at the upcoming schedule. Make sure that you already know these dates in your agenda. And for now, just grab some tea or coffee and relax, and we'll be starting the talk in just a moment. So we're going to start with the seminar. Just before we start, if you have any questions during the talk, just put them in the Q&A, and I will moderate the chat, and I will ask them for you. We are up. We're very happy to introduce Dr. Peter Clayson as today's speaker. Peter is an assistant professor at the psychology department of the University of South Florida, and his main research interest is at the border of clinical psychology and cognitive neuroscience, where he studies adaptive control in both healthy participants and psychopathology. Peter is also focusing on improving research methodology in clinical neuroscience, which is why we thought that he would be an excellent speaker for a RIOT seminar. He has a strong interest in psychometric evaluation of psychophysiological measurements and is a big supporter of using psychometric methodology to increase research reproducibility in psychological science and clinical neuroscience. And today, Peter will talk about multiverse analysis using psychophysiological data. So Peter, we are very happy that you can join us today. And the floor is yours, so you can share your screen and I will send everything live.
Awesome. Can you give me permissions?
Yeah.
To share screen?
Yeah. You should have them now.
Okay, how's that?
Yes.
Perfect. Well, good morning. Thank you very much for having me. I'm excited to be here and talk a little bit about the work we've been doing over the last few years. I wanted to start off with, well, kind of a fun fact about me. It also provides a good metaphor for my talk today. So one thing about me is that I really love to cook and bake. One of the things I like about cooking is that you can be pretty flexible with how you prepare the food. So, if you like garlic, go ahead, throw in more garlic. If you like cheese, the more the merrier. Pick different kinds of cheese. Why not? Cheese is delicious. Baking, on the other hand, I find baking to be a bit more troublesome. It requires a level of precision that is just not there with cooking. So one of my favorite things to bake is chocolate chip cookies. But if you've ever tried to bake chocolate chip cookies, they're actually pretty easy to screw up. So if you replace baking soda with baking powder, you get this flat, crusty cookie. It's not a very appealing looking cookie. If you don't refrigerate the dough before baking, you end up with this firm, crumbly cookie. It doesn't have that satisfying crunch on the outside and that gooey, fulfilling middle. If you melt the butter instead of letting it soften to room temperature, we've all learned this lesson the hard way, you end up with this greasy cookie. It just spreads out too much during baking. So if you want the perfect cookie, you have to follow all of the instructions precisely. You can't take shortcuts when you're baking. So if you follow the recipe as it's written, you're going to be rewarded with this beautiful, delicious cookie. So as you can see, baking it's not like cooking. You can't just swap out ingredients, change the orders of steps, and change proportions. This is why they call baking a science. And when you want to help someone else reproduce the perfect cookie, you provide them with the perfect recipe. So when we want to share our scientific recipes or communicate how to reproduce or replicate our findings, we have to write detailed method sections that communicate all of the important steps. It takes many, many steps to take files and files of these wavy lines like you see up here on the top right into something beautiful and interpretable and tasty, like these waveforms on the bottom right. This is my perfect cookie. But replication difficulties in psychological science have really focused attention on research practices that hinder replication, that contribute to these failures to replicate. And one possibility is failing to report all the necessary methodological information needed to replicate or reproduce your findings could lead to these problems with replication. Missing or ambiguous information could be important key ingredients of a study's recipe. So it's quite difficult to reproduce analyses or replicate a study if what was done in the first place is not clear. So such ambiguity or missing information, it can elevate false positive rates, especially in the face of undisclosed flexibility, because there are numerous researcher degrees of freedom in any study of neuroscience, especially in studies of using neuroscientific approaches. And collecting and analyzing event-related brain potentials, or ERPs, it's computationally intensive. It requires many, many methodological choices, and many of these choices are left up to the researchers. There's this one study, it's already a bit old by now, but it found that missing information, leads to wasted resources. So in the biomedical sciences, it's estimated that billions of dollars every year are lost due to misreporting information or to inadequate reporting of methods. So incomplete recipes yield undesirable cookies that just waste ingredients that goes into them. So in appreciation of these issues, many societies, psychophysiology being one of them, have published guidelines for studies of event-related brain potentials. So these guidelines help facilitate transparency because they identify the key ingredients that need to be reported in every single study so that the scientific community knows everything they need to in order to confidently replicate and reproduce your findings. So we had this question a while back: how well are these guidelines actually being followed? How well do science actually report their recipes? So we, for sake of transparency, pre-registered our recipe on Open Science Framework, generally that link at the bottom left. But here was our recipe for the sake of this study. We identified 5 journals that popularly publish studies that use event-related brain potentials. And then we grabbed 5 articles per journal per year for a total of 150 studies of ERPs. And we went through and we coded every single one of those studies. So here are the things that we were looking for in this project. So according to the guideline, there were these key reporting categories that needed to be covered in every single publication that reported ERPs. So you needed to have participant information. You need to report things like gender, age of participants, years of education, the number of participants in your study and in each group. EEG online recording parameters. So what was the hardware you used? What were the online settings that you used, like filtering or online references? Stimulus and timing. So which stimuli were used in your study? If you're using images from something like the iApps battery, which images were you using? What were the timing of those stimuli? Pre-processing procedures. So this is everything done offline. So offline filtering, ocular artifact correction, rejection parameters. How are your ERP measurements scored? Did you use a time window mean amplitude or a peak amplitude? Which sensors did you use for scoring? What were the statistics that you used in your study? Were they appropriately described? Did you check for any assumptions of those statistics? And then details about factor analytic approaches that you might have used in your study. So a parameter was only required in the study if the study needed it. So if the study described using ICA, for example, then they needed to describe how they used ICA. But if it didn't, that didn't count against the particular article. So what could this ambiguous information look like? Well, we had many examples after coding all these articles, but I want to give you a kind of a brief glimpse into some of the things we were seeing. So, EEG data were re-referenced. That's pretty unclear what was actually done after the fact in pre-processing. So a better way to describe it would be EEG data were algebraically re-referenced to average mastoids. You're providing the sites that you were using for re-referencing. EEG data were filtered from 0.1 to 30 hertz. There's a lot of missing information there. So are these half amplitude, half power cutoffs? What type of filter was used? What was the roll-off for the filter? ERPs were baseline adjusted. That's not enough information. I think a lot of articles assume that anything before the stimulus of the response was used in that baseline time window, but that's probably not a safe assumption, particularly for some of the ERPs I care about. Something like error-related negativity was scored between 0 and 100 milliseconds. So there's really important information there, like how was it scored? Was it a peak amplitude, time window mean amplitude? Which sensors were used for scoring? Was it a single sensor or multiple sensors? So we coded all 150 of those articles, and on average, only about 63% of the necessary methodological information identified in the guidelines paper was actually being reported in the study. And reporting behavior was similar across journals. And when you look at the range, I find it a little unsettling. So, on the low end, we have 39%, so less than half of the necessary information was reported in a particular article, but also at best, only 82% of the necessary information was reported in an article. That means not a single of the 150 articles we coded reported all of the necessary information needed to reproduce and replicate the findings based on this guidelines paper published in Psychophysiology. So I'll show you a little bit, what it looks like based on reporting categories. So here we have the percentage of parameters reported on the y-axis. Then we have the different categories on the x-axis. You don't necessarily need to pay attention to any particular pattern of effects. It's just interesting to see how we do better with some categories than we do with others. So maybe, as you might expect, we do pretty well with participant information, stimulus and timing. That was kind of a surprise to me. We're not doing too well with reporting everything we need to for things like ICA, or even ERP measurement or EEG recording. So another motivation of this particular study was to see, well, did the guidelines paper help? So that's why we coded articles from 2011 to 2013, and then 2015 to 2017, because we were curious, did the publication of these guidelines move the needle at all? And no, those bars are pretty flat. And the statistics confirm the story. Those are basically identical. We observed no impact of the publication of the guidelines article in 2014. On average, only 2/3 of the necessary methodological information is being reported in a given article. And we've actually updated these statistics a bit currently, and really it's still a problem. So we have this registered report. It has an in-principle acceptance. It's back under review. Well, it should be back under review very soon. And we're comparing behavior of reporting methodological information between pre-registered studies and the companion articles identified in the same journals. So we took, the preceding ERP article and compared the two. And so just for the sake of, I think it's interesting to see that on average, still only about 2/3 of the required information for confident replication is being reported. And this is across 181 additional articles that weren't reported in that original publication. And this is since 2019 up until 2014. So these replication rates are nearly identical to the study we published 5 years ago. So nothing's changing. It might warm your hearts a little bit, since this is an open science club, that pre-registered studies did marginally better. It was statistically significant, but only like 3 or 4% better. Like it was not as great as I was hoping it would be. So what this seems to mean is that there's this widespread of omission of about 1/3 of the parameters we need to replicate studies. This is a really big barrier to successful replication and the evaluation of research quality of the work that we've published. So it's unclear how to judge whether experimental procedures or data processing pipelines and collection are appropriate unless we have all the information in front of us. And just in case you're not an ERP researcher, you think this really isn't my problem, but this really is not unique to studies of ERPs, unfortunately. Maybe fortunately, because it doesn't cast a bad light on us. This is pretty common across subfields of neuroscience. Poor research reporting documentation is not unique to studies of ERP. And probably like the biomedical sciences, this leads to a lot of wasted resources and failures to replicate in our field. And those resources would probably be better spent on other studies or other endeavors. So one possibility why there is this widespread omission of important methodological information is that there's just maybe an underappreciation of whether these processing parameters actually matter for a given study. So maybe these aren't key ingredients to your scientific recipe. Maybe in the grand scheme of things for your chocolate chip cookies, it doesn't matter whether you use semi-sweet chocolate chips or milk chocolate chips. If you use white chocolate, those are going to be disgusting. So, I would stick with milk chocolate or semi-sweet. But the question is, does it matter? So that was kind of the motivation of this next study. So there are a lot of steps, as I mentioned before, to get these files of wavy lines into something beautiful and interpretable. And it takes a lot of work on the part of the researcher and many decisions on the part of the researcher to distill wavy lines into something we can use in statistical analysis. So we have to consider settings for high pass filters and low pass filters, not just cutoffs, but also family types and roll-offs. We need to consider eye movement correction procedures, whether you use ICA or regression-based approach, different approaches for referencing your data offline, different time windows for baseline measurement, different sensors used for scoring, and different actual measures themselves. Are you using different ERPs, different time windows for scoring? Are you using a peak amplitude or a time window mean amplitude? And this slide, I think, helps illustrate what a multiverse is. So a multiverse analysis respects the fact that a final data set that we have in any given study is the result of many decisions these decisions we have to make, but they're left up to the researcher. Many of these decisions can be not necessarily ill-informed, but more based on tradition than maybe best practices. So maybe it was the lab we were raised in as grad students, or maybe we're trying to replicate this particular study and we're going to do the same thing because it worked for them, so hopefully it works for us. Although they don't report all the information they need, and that's kind of unfortunate. But in an ideal world, maybe not an ideal world, but if these things don't matter, then we could choose any different settings for these different stages of processing and end up with the same result. But a multiverse analysis can help shed light on how fragile or robust different decisions are to a final data set. So I want to show you an example of a multiverse analysis we did for data processing pipelines using a study of error-related negativity. So error-related negativity, or ERN, is this negative deflection in the scalp-recorded ERP. It's larger or more negative for error trials than it is for correct trials. And it's relevant for performance monitoring aspects of cognitive control. ERN represents this manifestation of anterior cingulate cortex activity. And I want to introduce what it looks like just a little bit, and I use this scheme throughout the talk, so I'll walk you through it. So on the x-axis, we have time in milliseconds. On the y-axis, we have amplitude with negative plotted down. So in this particular figure, we're going to have error trials in red and correct trials in blue. That arrow there points to the deflection that we consider to be ERN. So it's a pretty robust difference between error and correct trials that happens within 50 milliseconds of an erroneous response. And it also has this nice, beautiful frontocentral scalp distribution. But these waveforms represent just a single instantiation of a multitude of possible data processing pipelines that we could have used that would all be reasonable and are all pretty common in the literature. And it's helpful to illustrate kind of what goes into an average ERN score in order to illustrate how we might identify kind of the best pipeline for data processing. So here are 6 real ERP error trials from a participant. As you can see, it's a bit easier to distinguish ERN on some of those. Maybe trial 3, trial 1, trial 4, those look pretty good. Trial 6 is pretty messy. So that shaded region there is that time window we use for scoring ERN. But we assume on any given ERN trial, there is a true signal among background noise, which is why averaging works for ERPs. So if we were to score these single trial mean amplitudes, we would end up with this nice normally distributed histogram. Well, that's pretty solid. That looks pretty good. So this participant made 69 errors. That's pretty normally distributed. And this is why the averaging procedure works. So we could quantify data quality for this participant by taking the standard deviation of those single trial means. So if that standard deviation were very small, that would mean the single trial estimates are all tightly clustered around the mean. But if it's wide, that means there's a lot of variability within that participant's data. We could also look at experimental effects. So I could plot for this individual participant the difference between error and correct trials. I could calculate a difference score of error minus correct in order to quantify the experimental effects. I think this slide is also useful for illustrating how challenging it can be to characterize data from a single participant. We ask a lot of our statistics and a lot of our numbers. But for the purposes of the study I'm going to talk to you about now, we're going to quantify or operationalize data quality as the standard deviation of those single trial means, and then experimental effects as the difference between correct and error trials. So we wanted to look at a multiverse of data processing pipelines. So we had almost 3,500 scores per person. And we were trying to pick the processing pipeline that led to the highest data quality, so the lowest between trial standard deviations, and the largest experimental effects, so the most robust difference between error minus correct trials. So this procedure is a very bottom-up approach for optimizing a data processing pipeline. So in this study, we had 298 participants complete a modified version of the Erickson flanker task. The data are posted there at OSF, at that OSF link on the bottom left. And this is the multiverse we looked at. So we only looked at a handful of different choices for each of those data processing stages. So for iMove and correction procedure, we just did one independent components analysis procedure and one regression-based approach, even though there are probably at least a dozen reasonable choices you could have made. And I think this is important to point out because I'm trying to emphasize that this is just a multiverse. I guess in the grand scheme of things, there are infinite multiverses. It sounds like a movie, probably a Marvel movie. But this is just one possible multiverse that we could have looked at. So if these choices don't matter, then if I were to plot these waveforms, all the different waveforms would just be overlapping. They'd be right on top of each other because any particular change in a decision shouldn't impact the resulting waveform all that much. But that really wasn't the case. So each line represents a different data processing pipeline. That arrow there points to the deflection that is ERN. And the correct trial ERN was basically the same. So we usually call that the correct related negativity. It's possible, however, that maybe these different choices might be shifting the waveform up or down just a little bit. And that if we look at the difference between error and correct trials, any differences would be, jittered out when we use a subtraction-based approach. But we still see quite a bit of variability in those different waveforms. So visually speaking, it does seem like these different data processing pipelines that we are using matter. Some of these pipelines are leading to larger error minus correct trial differences. Others are leading to smaller error minus correct trial differences. And if that's the experimental effect that you're interested, you're probably going to care a lot about this. So just for the sake of completeness, I want to show you the optimized data processing pipeline. So here are the different settings that we found, and I'm not going to go over any particular one. I just think it's interesting to include. So I've been emphasizing this kind of bottom-up approach to identifying optimized data processing pipeline, but there's still a need for a top-down discussion of what to do when you're selecting these parameters. So really, what is ideal? So only the region of interest approach to scoring ERN led to both high data quality and robust experimental effects. So that's kind of an easy decision make. Low pass filtering, eye movement correction procedures didn't impact the experimental effects all that much. So maybe you would pick the one that led to the highest data quality. For measurement approach, the peak amplitude showed the most robust experimental effects. But we know that with using a peak amplitude, Steve Luck has written a lot about this very clearly. It can mischaracterize the true underlying ERP peak in some instances. So a researcher might go ahead and continue using the time window mean amplitude. I know I do. And so even though we have this kind of bottom-up way for identifying this pipeline, we still have to try to understand why we're observing these differences. But it can help shed light on where we need to be looking. For this particular study, all of the settings we used are settings that are commonly used in the literature. There's nothing strange in there. But this approach helps illustrate how we can optimize data processing pipelines, at least for data quality and experimental effects, using this multiverse approach. So I hope it provides a roadmap for how to apply these multi-level models. There's a lot more information on the OSF repository for how to implement this on real data that others might decide to use on their own novel ERPs and data processing pipelines. But this multiverse approach only really picks at one decision point, I guess, kind of the many decisions that a researcher has to make, because a lot goes into any particular study. So you can imagine a person might have a research question about experimental effects related to error processing. And, this person might select a Stroop task, collect data on a bunch of participants, get all the files and get the waveforms. But there are more arrows in this step than just taking EEG into ERPs. And really, the multiverse analysis approach helps us shed light on why we make the decisions that we do. So we've tried to understand how some of these other decisions might influence our ERP scores that we care about. So we've looked at, for example, how different tasks might relate to differences in ERPs. There's a fairly, I wouldn't say it's a common assumption in the literature, but it kind of seems to be when people are interpreting findings from different ERN studies that, the ERN is the ERN that is the ERN. So if you record ERN, it's the same in your flanker task as it is in your Stroop task, as it is in your go, no go, or something else. So we decided to see whether this is the case. And we collected data during a flanker, Stroop, and go, no go task, and we observed differences in ERPs. We observed differences in internal consistency. Maybe that doesn't matter all that much. But once we try to relate it to something functional like behavior, it helps kind of clarify that maybe there's more going on in any particular task that is leading to differences in ERPs than just chance differences. So this study was conducted in, I believe, almost 200 participants. All participants completed a version of the flanker, a version of a go-no-go task, and a version of the Stroop. And we're relating ERN scores from the previous trial to response times on the upcoming trial. In blue and red, flanker and Stroop, we observed that as ERN gets larger on the previous trial, response times get larger on the next trial. But we observe an opposite pattern, an opposite slope in the go-no-go task. So a larger ERN actually relates to faster RTs on the upcoming trial. So there appear to be, at the very least, in these relationships between ERN and response time, differences across these tasks. Not just differences in the size of the effect, but the direction of the effect. So the relationship between ERN and response time is different in go-no-go tasks than it is in a flanker and a Stroop task. So the selection of the task you use for your particular study of ERN does not seem to be a trivial decision. And we have, explored this across different versions of, for example, flanker tasks, because, the flanker task is not this reified, unitary task that everyone uses. We all have different versions of it. There are many different versions of a Stroop task out there. And these differences in the tasks that we use relate to the differences in ERP scores. And what we're trying to now understand is why we observe these differences across tasks and different versions of the same task. And maybe there are better tasks for studying, for example, something I'm interested, like ERP relationships with psychiatric symptoms, than studying something like ERP relationships with behavior. We don't know because we've kind of largely neglected this area of the multiverse. And it's not as small as I'm letting on. So, we've been focusing really hard on error-related negativity, but there are a lot of ERPs recorded during even a flanker task or any number of these tasks. So we looked at, and this was in a collaboration with Miranda Lutz, and we're looking at the different combinations of previous trial ERPs and current trial ERPs and task effects and how they all uniquely predict response times. So we tested something like 6,000 or 7,000 different models, identified the optimal model to try and understand, do these different ERPs uniquely relate? Because typically in a study, you only focus on one or two scores. So here you don't need to pay attention to any pattern of effects, but if it's red or blue, that means that the credible interval excluded 0. So we're interpreting that as that particular ERP is influencing uniquely the response time. Those gray lines mean that the credible interval included 0. So all of these ERPs to these different trial types are uniquely predicting current trial response times. And this is even after considering those kind of conventional task effects like congruency effects or accuracy effects. So what we choose to focus on is really only one small piece of the whole puzzle. But when we focus too much in on that one piece, we're neglecting a lot of important information. So I'm particularly interested in psychiatric symptoms. So I tend to use an RDoC-inspired approach, look at the transdiagnostic relationship between ERPs and symptoms. And one of the more consistent relationships in the ERN literature is its relationship with anxiety. So ERN has been proposed as a neurobiomarker of anxiety and a risk for developing anxiety disorders. And even though this is considered one of the more consistent relationships, there are about 6 meta-analyses, with different inclusion-exclusion criteria, and across these meta-analyses, they're concluding that basically there's no relationship between ERN and anxiety to, maybe a modest relationship. Because everyone's kind of, picking their own inclusion-exclusion criteria. Maybe these different things are, key. And so this seems like a beautiful area to apply multiverse analysis. So the multiverses I've been talking about so far have really focused on kind of experimental design and data processing. So for this particular study, we're going off that same kind of flanker Stroop go-no-go task I talked about before. But now we're going to focus on outcomes. And this is kind of where multiverse approaches kind of became more popular in the social psychology literature. So instead of just focusing on one eventual outcome to look at your data, take them all. See how fragile and robust your finding is. So we considered a handful of experimental procedures and data processing pipelines, and now we're considering different outcomes for anxiety, different clinical groups, different ways of slicing up those groups. And then sex is this popular moderator in the literature. And this is just meant to illustrate the multiverse approach. I included this analysis in the review paper I wrote this year. This isn't meant to like really be a one-all be-all. This is a pretty healthy sample, but it illustrates the multiverse analysis approach and its application to kind of the distribution of p-values, I think, pretty well. Because the way you can interpret these multiverse outcome studies, as has been used in the social psychology literature, is you're looking at how fragile the effect is. So you plot the p-values for all the options, and you focus on how the distribution looks. So if the distribution is pretty flat, then that means you probably have a pretty fragile effect. That means your particular choices matter a lot or not at all. That probably means that maybe we're capitalizing on researcher degrees of freedom when we're looking at these relationships sometimes. So if I'm looking at different measures for looking at the ear and anxiety relationship, that doesn't seem to be the significant moderator of what's going on. If you look at different ways of identifying clinical groups, it's interesting here that when we use the PSWQ to identify clinical anxiety, which is not an approach I recommend, we would do a clinical diagnostic interview, but for the sake of illustration, I think it's helpful. It does seem like the p-values are clustered under 0.05. So maybe this is a more robust effect for anxiety groups defined using the PSWQ. And here is our sex moderator. Interestingly, we see this cluster of p-values under 0.05 for males, which is the total opposite of what's being seen in the literature, that it's primarily a relationship between ear and anxiety in female participants. So what do we do with all this multiverse information? Well, there are many different multiverse approaches that you can use to see how fragile or robust your effects are. You can look at different data processing parameters, different outcomes. There are so many different ways to categorize anxiety disorders, for example. And you can see how robust or fragile your effects are to those different choices. I think what multiverse approach really sheds light on is transparency in how we're doing our data analysis. The danger is, when researchers are led down the garden of forking paths and they pick the outcome that leads to the statistically significant effect, because that's probably pretty easy to do when there are so many choices available to us. Maybe, this researcher has just identified the best way to look at the relationship, or maybe they're just capitalizing on chance. So which processing parameters would maximize individual differences? And most of these is focused on group-related differences. I'm particularly interested in things like psychiatric symptoms and relationships in clinical groups. But hopefully, the posting of this data processing code and the analysis procedures can help others apply this approach to novel paradigms and ERPs that I just haven't even thought of. So my hope is that over time, applying this multiverse analysis procedure in different data sets will help shed light on the key decisions that matter for the data outcomes we care about. So this might support efforts to standardize data processing pipelines for particular ERPs or particular applications. In some ways, I think this sheds a bit light on how it might be a bit premature to rely on standardized data processing pipelines without understanding how all these different data processing decisions can influence the scores that we ultimately care about and ultimately used in our statistical analyses. Regarding methodological information, there are probably three groups that care about this the most. Here are our three stakeholders: authors, editors, and reviewers. I'm not sure how much responsibility lies with each party, but as things are now, they don't really seem to be changing. So, we've presented data basically from 2011 to 2024. About 2/3 of information is being reported that we need. Things are pretty consistent, so authors are not reporting this information. So it seems that editors and reviewers need to do their part a bit more in enforcing these guidelines. And it's a lot to ask of editors and reviewers who are already so busy with all their work. But it doesn't seem that there are going to be changes in reporting behavior until there are requirements to do so. So the guidelines paper I mentioned before from SPR and published in Psychophysiology, has this nice checklist at the end. These guideline papers are important to follow. They're trying to identify all the information we need to report in our study. So this checklist, these methodological guidelines papers, there are a handful of these, could become similar to PRISMA guidelines for meta-analyses. They could just go hand in hand with any ERP study. You just include this checklist with your study of ERP and have it at that. It's also possible that maybe there's just, let's be honest, there are space limitations in many of the journals we publish in. You can only say so much about your methods with 4,000 words. So, you can always publish information as supplementary material. You can always publish more information on Open Science Framework, including, for example, the checklist from a guidelines paper. I think pre-registration and registered reports are helpful for identifying potentially relevant methodological information and the parameters you need to consider, because you have to spell out, or you're given the opportunity to spell out what you plan to do before you actually do the study. So you need to think a little bit more carefully about the different data processing decisions that you're wedding yourself to. And planning how the data are going to be collected and analyzed will hopefully give greater attention to these different choices and the different quality checks that might be necessary. Another barrier to reporting could be that researchers don't really know the specific ways in which their data were processed. So prepackaged code can kind of become a black box. It is really helpful to have this prepackaged code, but if we rely too much on these software analysis packages to do the work for us, we start to lose track of what's being done. So to the extent to which these software packages can include validity checks, would be helpful for researchers who are not necessarily readily able to judge whether the data processing pipeline is appropriate for the data at hand. Some of these software packages include processing summaries, which I find to be really helpful. They include printouts of what was actually done. Ideally, these processing summaries would kind of mirror these data guidelines papers, because simply saying that you use the software defaults really isn't all that helpful. Because I don't know what the software defaults are. I don't want to have to track down the software package, and things might have changed in more recent versions of the software, and it might not be readily clear unless you kind of dive into the version history of the software. Along similar veins, I think sharing of pre-processing code and experimental paradigms will also help communicate what was done in any particular study, because all the steps are laid out in the script. Although I would not consider this a substitute for reporting all the necessary methodological information, because not everyone can be an expert in all the software packages. So, hopefully the code is really well commented and, plain ERP language, like what the filter is doing, what type of filter, what the cutoffs are, what they mean. Because even when I look at code I wrote 10 years ago, I have a hard time understanding it because I'm using different software now. I'm not as versed in whatever package I was using before as the package I'm using now. And it's possible in 20 years, none of us will be using anything that we use now. So publishing the code won't help us all that much, but maybe ChatGPT will help interpret it for us down the line. So the take home, I think, is that we can really be doing more. We have room to improve in the communication of our scientific recipes. So an average reporting of a third of the parameters missing is pretty bad. On the one hand, we're reporting 2/3 of the necessary information, but on the other hand, not a single study is reporting everything that we need in order to replicate scientific findings, in order to reproduce a particular study's analyses. Multiverse analyses, I think, can be a helpful approach for identifying the key ingredients in our recipes. So these multiverse analyses can help identify the best tasks for our research questions, the best data processing pipelines, the best ways to analyze our data, but it's only one tool. So like any other tool, it's just appropriate for what it's appropriate for. It's a very bottom-up procedure. It's not really going to help us understand why we observe differences. That we still have to use our head for. But my hope is that by clearly describing our scientific recipes and identifying the optimal parameters and ingredients for our scientific studies, we can all bake and eat these delicious cookies and enjoy the fruits of our labors. So I want to thank my collaborators for all their help. I want to thank you very much for your attention, and I'm happy to answer any questions you might have.
Thank you, Peter. It was great. Thanks. So if people have questions, feel free to put them in the chat. I, of course, also have some questions. Because I was wondering, you were talking about the people report too little of these important parameters. And I completely agree that writing these guideline papers are of high importance, because otherwise people are just going to cherry pick what they think is important for their audience, right? But how do you, what is your view on how people actually gonna adopt these guidelines? How are they gonna actually follow them? How are we gonna make this cultural change that people are actually doing this, right? Because I think only having a guideline paper out there is not enough. People actually need to be aware of these guidelines, I think. What are your views on that?
So I really think it's up to the peer reviewers and the editors to take a close look. Coding these papers though is not a trivial task. It takes like, if everything's reported very clearly, it can take maybe 10 or 15 minutes to code a paper, but some papers are really dense and hard to follow using maybe more advanced procedures, and it takes a lot longer. So it's a lot to ask of the editors and reviewers. My hope is that maybe these checklists would become more common. Yeah. I know Angela Socic, she has the Artemis project, which helps kind of, you basically put in all your data collection procedures, and then you just link to it every time you publish a paper. So all that information is there, because many of the different settings we use in a lab don't change. My hardware is my hardware. I report the same paragraph basically in every study I publish. And so this provides all that more detailed information about timing and processing that might be helpful and make it easier to communicate. But otherwise, I'm kind of at a loss, because the guideline papers make it very clear. I'm hoping that these kind of multiverse analyses help shed light on these decisions actually do matter. We should probably pay a little more attention to it, but it takes more work from not just the authors, but also the peer reviewers and the editors.
Yeah, kind of a cultural shift, maybe completely. We do have some other questions. One that I also had. So how do you, during a multiverse analysis, how do you decide? I'm guessing this is also one of the most difficult questions. How do you decide which and how many different decisions you want to compare? I'm guessing this comes down to domain knowledge, but I'm not sure.
Sure. I mean, it's kind of up to you. These are, we basically chose kind of the pipeline that's kind of outlined in the guidelines paper, kind of these key things that need to be reported in every particular study, and then try to grab a few different levels of each of those. We looked at different papers that have studied ERN and kind of what are the different settings, parameters that they're using, but it's going to vary widely based on the measure that you're interested in. So if you're looking at error-related negativity, you're going to use something very different than if you're using P50 than if you're looking at auditory brainstem responses or something else. So it's going to kind of be up to you, and not just the parameters that you think are important, but maybe the parameters that everyone seems to be neglecting.
Yeah.
If everyone's assuming that it's all the same, that's a great study to do, because people will either be really happy that you've shown it doesn't matter, or they'll be really upset that you've shown it does.
Yeah. And I was also thinking about, so you've touched upon this a little bit in your, you talked about using different types of the same task, basically. But I was wondering, where does it end? So, for example, maybe stimulus color has an effect, or your environment in the experimental room, or temperature. I don't know. So where does this end? Because it feels like you're going down a very, very deep hole, and you're trying to test out every single option. Yeah.
Yeah, for sure. I'm not sure where it ends. I imagine it's going to be very different for whatever particular study you might be interested in. I have a collaborator who's very interested in food-related research, and one of the things she really cares about is how hungry people are when they come to the lab, and it's just not something I've ever considered for a study of ERN. So I think trying to kind of pick the low-hanging fruit on what we might think is most related to maybe the psychiatric symptoms, the neurological disorders, or the experimental effects that we care about, kind of starting there. And the hope being is that we kind of come up with, maybe different paradigms that we think are like solid. This is a good paradigm for identifying experimental effects for ERN, has good internal consistency, but we don't want to be too prescriptive. We don't want to restrict exploration in any way. But it's really helpful for someone who's new to say, looking at studies of ERN, to start with, say, the flanker task in ERP core, because it's ready to be implemented. And, we know it works.
Okay, so we still have time for a couple of questions, I think. So in your own analysis of these ERPs, what were the choices that had the highest impact or lowest impact?
The choices that had the highest impact for ERPs, I think, really had to do with the task used for recording. We found we're a little upset by how little convergence there is across these different tasks. So we have this great replication study we did with Anya Riesel of her basically convergent discriminant validity paper published in 2014. And it looked at ERP relationships across flanker, go, no go, and Stroop. That's where a lot of these data came from. And when we look at the correlation across these tasks, even after adjusting for measurement error, like the correlation only hangs out around 0.5, 0.4 for some effects. Like that's leaves a lot of unique variance to each task. And we are still trying to figure out whether that's meaningful signal. So it seems to be the case. Maybe if you want to get a really good estimate of ERN, you need to collect it and during a few different tasks in order to get out the methodological noise that has to do with how you recorded it in order to kind of identify this latent construct that is ERN or error monitoring or whatever it is. But I think that's one of the most neglected considerations, even though there are some big meta-analyses that show that task moderates effects in relationships with things we care about.
Great. And then I have another question. Thanks, Peter, for your talk. Great recommendations and insight from your research. I want to add, especially to the grad students, to have the courage and explore your data beyond your typical pipeline. Only by explaining what the implications are from the traditional decisions, you will better this research. And I'm curious about something. How can a grad student looking at his or her data know when to explore optimizing their pipeline without being the person that is fishing for results?
Well, I think it kind of, I always encourage graduate students to play with everything. I always encourage them to break stuff so they have to fix it. Tweak the code so you understand what changing that line does to your data. Because I think that exploration is really an important pedagogical experience for understanding what these different steps do to the data. So even if you're not planning to do this complex multiverse analysis, we'll see what different filtering procedures do. Write your own filter. I remember it being a really illustrative experience for me when I was in grad school when my advisor made me write my own filtering procedure, because then I realized, like, wait, what do I do with the data in the shoulders? Like, I don't have enough data points to filter. And he's like, well, different processing software packages do different things. So then we kind of discuss those different things that different software packages do. So I think it's just kind of important to, just start looking, and maybe it'll give you a sense, explore, and then conduct a new study and see whether that exploration pans out.
Okay. I just hear from final question. How realistic is it to find one standard pipeline if so many decisions are lab dependent, like hardware and participants?
Pretty skeptical of standardized pipelines. I just think a lot of these decisions matter. I don't think there's one tried and true approach for all ERPs, especially all ERPs. Maybe for particular ERP components, there are decent data processing pipelines that you can be confident in, even though it might not lead to the most optimized score. So maybe that's more of what the data processing standardized approaches are pushing toward, kind of a safe pipeline rather than a best pipeline, because all these decisions seem to matter. It's not going to work for every single ERP, but we also don't know until we check ourselves.
Yeah. Okay. I think that was it for the questions. Thank you, Peter, for this great talk, and everyone at home for attending and giving us the questions. I do want to highlight our final our upcoming talks. So our next talk will be on January 20th, and it can be attended in person again. It will also be broadcasted online. In the meantime, feel free to share anything that we post or send with anyone. The riots are open to all, so we'll be happy that more people will find us. Also, if you're interested yourself in joining the RIOT Science Club, reach out to us and we'll get in contact. So again, thanks everyone for attending, and we hope to see you next time.